Hi everyone, welcome to the Organic Chemistry Seminar for Term 2. The idea is that this builds into Term 3, so for Term 2, you'll be doing Organic Chemistry. You'll be doing a little bit of Industrial Chemistry as well, but that comes into the third unit, so into Term 3 to finish Unit 4. The whole idea is that you're not just learning about stuff anymore, you're actually learning about synthesis of materials, how to build things, how to increase yield, how to reduce waste. Most of you guys watching this are my chemistry students anyway, so you've heard me rant about green chemistry and things like that. This first week will be an overview. We'll go over intermolecular forces, everybody's favorite, and then we'll go over hydrocarbons as well and see how we're going for time. But what I really want to do is make sure that you guys understand the fundamentals of intermolecular forces. If you don't understand intermolecular forces, there's no point going beyond this week. My wife often jokes in organic chemistry courses at uni, if you didn't know the answer and you wrote intermolecular forces for the answer for an organic chemistry question, you would be vaguely right. And it's true because they are the backbone of everything that we look at. Even in the industrial chemistry, when we look at polymers, and proteins, and carbohydrates, and fats, all those kinds of things, if you understand intermolecular forces, you will be able to vaguely look at and look and see what's actually going on. So today will be intermolecular forces, the 12 functional groups, then maybe we'll get on to hydrocarbons as well. I'm not going to do all the fluff stuff that your teacher will do, and this is why we use carbon, blah, blah, blah. Not interested. We will get into what you actually need to know. Get rid of everything you've done. This week, there won't really be any exam questions because it's just an overview of stuff you've really already done. As of next week, when we start naming things, we start looking at solubility, melting point, that's when we'll actually work through some exam type questions. And I'm using the exam from last year as an example, so it's relevant to what you're studying now. So I want everyone to take 30 seconds or so on my whiteboard to think about what intermolecular forces are. If you sat there in the live now, you can type it into the chat. What are they? What do they do? What does it mean? And if you are watching, go to your formula book, which I will continually reference through this. Don't mind the police siren in Townsville. It's a never-ending feature. If you go to your formula books, and can always have it, because I will always refer back to it, because I want you guys for your exam to be comfortable using the formula book. There is no point having that formula book if you spend half the time, oh crap, what's on what page? What does this mean? Because you will waste so much time if you don't understand what is actually in that formula book. And Poppy just dropped off. Okay. So we are going to look at intermolecular forces. They underpin everything you need to know in organic chemistry. Finish up this. Ross and Holly, I expect you guys to know what intermolecular forces are because you're my students. And if you don't, you'll make me look really bad. I just use IMF because I'm lazy. Come on, Ross, don't let me down. The less you answer, the more I'm just going to randomly call you out. So, intermolecular forces is all to do with electronegativity. And that would have been really impressive if I could remember the page number that was on your formula book, but I'm not quite that smart. So what everybody, if you don't have your formula book, Google search for QCAA chemistry exam formula book, something like that, and it'll come up. Why is it important? So electronegativity tells us when we have two elements that are bound together, will one of those elements hog the electrons in, and we're talking organic chemistry, so we're talking covalent bonds. when they're sharing the electrons, will one of them be negative or hold the electrons and the other be positive or not hold the electrons? So if we look at a non-polar bond. Anybody remember back to grade 9? They learned about ionic bonds and polar covalent and non-polar covalent. So I want you to think of a magnet. I meant to buy a magnet today to visually demonstrate this. But a magnet has a negative and a positive end. It's a beautiful picture of a magnet. Hopefully that's not your grade, C-. I'll stop making terrible jokes now. So non-polar. So polar molecule has a positive end and a negative. When it's non-polar, we have what's called an even distribution of charge. The electrons are evenly distributed. Or if we have hydrogen bound to carbon, the electrons are evenly distributed around this molecule here, meaning there is no permanent charge on either end. How does this relate to organic chemistry? It really big time relates to organic chemistry. So if we have hydrogen bound to carbon, what I want everyone to do is find the electronegativity values for hydrogen and carbon in your formula book. You have 30 seconds when you're going to stand here awkwardly and stare at me. You're watching the recording, everyone just disappeared. I'm just letting everybody think. Okay, so the electron, I might get this wrong, carbon is 2.6, hydrogen is 2.2. So the difference between them is 0.4. In order for a bond to be polar, i.e. one of the atoms will hog the electrons, the electronegativity must be greater than 0.5. Now, this is extremely important to remember when we start looking at the functional groups in organic chemistry, because it will tell you everything you need to know about the organic molecule. So that's non-polar, or what we call in organic chemistry, we call them dispersion forces. So when we have a non-polar molecule, we get dispersion forces between the non-polar molecules. So what that means is, when we look at, so let's say we've got, so we're looking at carbon and hydrogen, two molecules, carbon and hydrogen. It's a non-polar bond because the electronegativity difference between them is less than 0.4. That means that the electrons are evenly distributed around the atom. But we should all remember back to grade 7, grade 8, when you look at protons and neutrons. So the electrons that are floating around may not always be, hydrogen has its 2 electrons. If they're over this side, then this side of the hydrogen atom has a positive charge because of the nucleus, the protons in the nucleus. This guy, his electrons are over this side, giving this side of the electron atom, the hydrogen atom, a very slight negative charge. Now what happens when we put a negative and a positive end of a magnet together? That's killing me, my voice is going to die. We get dispersion forces, if I can spell properly, between the hydrogen atoms. They are weak. So they are the weakest intermolecular force that we look at in organic chemistry. They are also fleeting. I think that's the term I use. Fleeting. Because eventually, these electrons will move back around and that bond will break. So, does everybody, do you just give a thumbs up with Zoom? Everybody, that makes sense for everybody? Okay. Made so much sense to Holly, she laughed. Well, she has bad internet. Okay, so I'm going to grab a tissue to wipe that off. All right. So now, let's move into, so remember when we start looking at the functional groups of the organic compounds, it's in a slightly different order to what your teacher will do. But I've been doing this for a while and I think this is a better order. Kind of flipped what I normally do on its head because hashtag YOLO. So remember, carbon and hydrogen, we have dispersion forces because we have non-polar bonds. So the next one we're looking at is polar bonding. Or dipole forces. These are the kinds of interactions that occur between polar molecules. So, polar bonds, dipole forces. This is when we have an electronegativity greater than 0.5. So let's look at carbon and oxygen. So again, go to those pesky formula books that everybody hates. Find me the electronegativity values, or for yourself, between carbon and oxygen. I bought 11 new whiteboard markers for this seminar, and I'm still using old. We'll break those out when we need different colors. So carbon should be 2.6. Could make it right to myself and get these wrong, but I'm pretty sure they're right. And 3.4. Giving us a difference of 0.8. So we know if we see, I'm going to give you a massive hint because you'll see this on about 5 different functional groups. And we have what's called a carbonyl group. So carbon with a double bond to oxygen. What happens here is oxygen, and this is, I had this argument with the teacher today who said that you didn't need to be a science teacher to teach grade 7 to 10 science because it's easy. My argument was the amount of stuff that I reference here, going back to grade 7 and 8, none of you remember it, ever. Because very few of your science teachers in high school were actually science teachers. They were just reading off the curriculum and the PowerPoint slides that they were given. So now I'll try to undo 4 years of bad teaching. We know that carbon and oxygen will create a covalent bond. They're sharing their outer layer. Oxygen has 6 valence electrons. 6. It's in group 6, I know, mind blowing. Oxygen, carbon, group 4. Shock horror, carbon has 4 electrons. Now in a covalent bond, oxygen only needs to give 4 of its valence electrons to carbon. Why is that important? Because that means that oxygen in a bond, a double bond with carbon, has 2 unbound electrons. It's hiding them from carbon, and they're just sitting, floating about, not used in this double bond. What we need to remember is that oxygen has the higher electronegativity. So of those 8 electrons that are floating about, 6 of them might be up here and 2 here. That gives the oxygen a very negative charge. I never understand why they write the negative with a line and then VE, but I still do. Carbon has loads of protons in its nucleus, 6 of them. So it's really positive down here. Now, if you take a weak magnet, stick it to a weak magnet, you could just pull them apart. What we've got here is a supercharged magnet. Now the bonds are stronger. They last longer. Because what we've created is a dipole. Di being 2, poles being negative and positive. So what does that mean? That means that if an organic molecule has this, the intermolecular forces present are higher than that if it was just carbon. All right. So now we're getting up into the real stuff. That makes sense to me. Poppy, congratulations on your economics mark, by the way. I only take 60% of the credit. No, it's good. Okay, intermolecular forces. Now we have hydrogen bonds. Anyone want to hazard a guess as to what there is, what happens with a hydrogen bond? It involves hydrogen. Shock horror. I know. So this occurs when we have hydrogen bound to either nitrogen and fluorine. And whilst you're going through your formula book, find the electronegativity values and the differences between these and let me know what they are or not. So, nitrogen, I always get nitrogen, I'm pretty sure it's 3.0. 0.8, just like oxygen. So we then have 1.4. Yeah. We now have a seriously big difference between them. Same thing happens. Nitrogen ends up with 2 unbound pairs of electrons. Oxygen ends up with 3 unbound pairs of electrons, and fluorine with, it's a lie, oxygen with 5 unbound electrons, fluorine with 6 unbound electrons. The moral of the story is the more negative this end is, the stronger the bonding. So if we were to draw out water, classic example of the hydrogen bond, we have oxygen, dirty electron thief. So he's got 2 extra electrons up here. Also hogging the electrons from the hydrogen, they become positively charged. The oxygen becomes super negatively charged. It's gone through a bad breakup. It's really negative and bitter about the world. Then another oxygen comes along here. Oh, hello. Look at my negative charge. We should bond together. Ooh. Another one comes along. Ooh, and we get the difference between this and polar bonding is that this uneven sharing is permanent. So we create a permanent dipole. In the event of like things like water, you have to boil water to break the molecules apart. Jacob. Hi, Jacob, you turn your camera off for me because it's being recorded, please. Okay, so pretty sure we've been through this, Jacob. We're going to the intermolecular forces present in all of the organic compounds. We're now at hydrogen bonding. When you see oxygen bound to hydrogen, when you see hydrogen, so mad, bound to oxygen, nitrogen, or fluorine, we have a hydrogen bond present. They are the strongest. It's a permanent bond. that requires a lot of heat, a lot of energy to break the bonds apart. Now, everybody gets a bit confused with intermolecular forces are not the forces holding the oxygen and the hydrogen together in this molecule. It's the forces holding the hydrogen here and the oxygen here, holding them together. They are still separated, but because of this electrostatic charge, they're held together by these bonds. All right. Now, let's look at all of the lovely functional groups you'll be expected to remember. Who's excited? Anybody know what a functional group is? In the chat, go mad. No, I can't remember what else. Functional group, part of the organic molecule that gives it its chemical and physical properties. Now, you may have seen something like this. You probably should have done it in grade 11. And we will go over this in more depth. Should have done this in unit 1 maybe. The structure of alkanes, benzenes, aromatic cyclic compounds. So all of the organic compounds are based off this. This is what we call a hydrocarbon. And your teachers will tell you this is the biggest, scariest, hardest of all the units in chemistry. I think unit 3 with all of your gases, equilibrium, all of the mathsy stuff for the electrochemical cells, I think that is much harder than this. Personally speaking. And I'm a senior maths, will be a senior maths teacher very shortly. I find this easier than the mathsy stuff that you have to do. But it requires you to learn everything, and anybody that's done a session with me will know that we learn it in a very sequential order. Each part builds onto the next part, builds onto the next part. Problem at school, your teacher rushes through it, you're not quite 100% sure, and then you try and do the next part, but you haven't learned what came before, and it snowballs into this stressful wreck. So what we're going to do is we're going to get ahead of where you are at school, so you can get to your teacher, and you can be a real know-it-all smart. So this is a hydrocarbon. I'm not going to go into what it is or why. Just this is it. This is it. This is a hydrocarbon. And while I'm doing this, I expect you to draw them, because the more you draw them, the easier it will be to remember. Give yourself the most amount of time you can to remember. So this is the hydrocarbon. In all its glory. It's called a hydrocarbon because it's hydrogen down to carbon. Yeah, that's very technical. We have here, what we have here is we have the alkane. The very first functional group, well, alive. It's the simplest organic molecule that we have, and all of the other organic molecules build up off this right here. The functional group of an alkane is the fact that it doesn't have any functional groups. Yes, that's weird. It doesn't have any functional groups, but its lack of functional group is what gives all of the alkanes their chemical qualities. No functional group. It's like a functional group is its functional group. Okay. The next one we have is pretty much identical, but between two of the carbons, instead of having a single bond, we have a double bond. And we call this one an alkene. And if you're wondering, I know the big question, do they only have dispersion forces or non-polar bonds? Yes, because it's just carbon bound to hydrogen. We then have the alkynes, which are now we have a triple bond between two of the carbons. Who remembers Lewis dot structures from their grade 9, maybe grade 10? Depending on the teacher. So each carbon atom must be surrounded by 8 electrons or 4 electron pairs. Each of those lines represents an electron pair. In an exam, you will lose marks if you have hydrogen here, hydrogen here, and hydrogen here, because it's incorrect. Because carbon only needs 8 electrons, and it's got 2, 4, 6, 8, 2, 4, 6, 8 on both sides. And with an alkene and an alkyne, their functional group for an alkene is the double bond. Functional group for an alkyne is the triple bond. All right. I'm not going to spend too much time going through these because you will learn them and understand them over time. Remember, everything builds off about alkane. So the next functional group is we take away a hydrogen and we attach a bromine. Or we're going to attach an iodine. We could attach a fluorine. We could attach chlorine. And again, very creatively named, we call this a halo. Because we have a halogen attached to an alkane. Mind blowing. Okay. So this one, next one, crazy idea. We add 2 bromine and it becomes a dihaloalkane. If we add 3, comes a trihaloalkane. You can see where this is going. 4 is a tetrahaloalkane. The idea is it's a halogen or 2 halogens, 3 halogens attached to our alkane. The next one. So what we have here, we're looking at now with our alkane, is we have a fuel that's currently inside your gas bottle, so propane. if I add an oxygen onto one of my hydrogens, I get an alcohol. So the thing your parents tell you to stay away from is one oxygen atom away from the fuel that's powering your barbecue right now. We have a hydroxide or hydroxyl group. I hope you see the pattern. It doesn't take much of a change away from our alkane to create something completely different. So I want you to take take a second to think what kind of bonds will be present here. Those three intermolecular forces we talked about. It will be hydrogen. We have oxygen bound to hydrogen. So now we're getting funky. We've added, do that in red so it stands out. Now we've added double bond with oxygen. What we call this is a ketone. Or we call it a carbonyl group. And in this instant, the organic molecule is ketone. I am not expecting you to remember this after one go. Even 2 or 3 goes. Is what we'll do is we'll go through them here. Next week we'll go through naming them all. It's just showing up. I'm not sure if I'm going to do or not. I've lost my icon. 40 minutes. Okay. So ketone, we've got a carbonyl group, which is just a carbon double bound to oxygen. So, what are ketones? If you're diabetic and you don't eat enough sugar, or you take too much insulin, your pee and your breath smells like paint stripper. Because your body, when it breaks down fatty tissues, you might have heard if you're into like health and fitness, the ketosis diet. Ketones shouldn't be present in the body. This is what happens. Your body breaks down fat, which produces ketones. Your body does not like doing that. So the way that I remember this, right, because we have ketones, we have the oxygen, it's attached to, this is attached to 2 carbons. So carbons, 2 carbons is a ketone. If we were to put this functional group on the outside, so here, it would no longer be a ketone, it would be an aldehyde. aldehyde because it's attached to a H. So if you see the double bonded oxygen in the middle, it's got a carbon on both sides. It's a ketone. It's attached to carbons. If you see this on the outside, it's an aldehyde because there's a H. It's trying to hide from this carbon over here. Again, not expecting you to know all of these straight up. You certainly will by the end. If not, I'll say no. So now we're getting into the more complicated ones. Another thing we're going to learn about, possibly in term 3, maybe at the end of term 2. Depends how quick your teacher is a teacher organic chemistry. Quick tip, the faster your teacher goes, means the less they understand. They're just trying to get through it without you asking too many difficult questions. I shouldn't generalize about all teachers, but I get to do that. So now we're getting into so if you see nitrogen attached to 2 hydrogen on the end of an alkane, what we have is an amine. Now, the amines, they are multi-trillion-dollar molecules, right? So, and not in a good way. This isn't condoning drugs. But amine, we have methamphetamine, we have morphine, we have benzodiazepine, or commonly known Xanax and Valium, various things you hear on rappers rapping about these days. So your amines are your biologically active drugs that are active within the brain most of the time. So if you want to go on and do pharmacy or medicine or biomed, when you finish, you will get to know these very well. Again, these are closely linked with what we would call an amide. Now we're mixing the functional groups. Now this entire thing is the functional group. We call this an amide. Again, mostly very biologically active in the body, being the center of some medical controversies, such as thalidomide. When you actually understand what these compounds are, you kind of look at medicine names and you go, oh, I know what that is. Maybe it's just me. Probably just me. An amine just has the nitrogen and 2 hydrogen. The amide has all the funky extra bits. All right, what else have we got? Oh, we have the back to our alkane. That's what I want to drill into everybody. So the only thing you take away from today is that everything starts with this, and then we build on it. What you have to do in your exam last year, and the content is exactly the same this year, it was in 2019, 2020, will be again this year, is you have to take an alkane, 2 alkanes, and make them into an ester, which is something again we'll learn about. But that's the pinnacle of this unit. And it's not anywhere near as hard as you think all of your teachers will make it out. So, right. What else have we got? So we now have what we call carboxylic acid. So that's the functional group for an ethanoic acid. We have oh, it's an alcohol, except it's got this under this one. It's a carbonyl group, I shouldn't just say this. Oh, getting old. You might know these guys. They make vinegar. Tastes like vinegar. Ethanoic acid is what makes vinegar vinegar. It also has a really high boiling point because of some weird properties where there's a hydrogen bond. All right, now we're getting weird. I think that's everything except for an ester. Yeah, starts to get a bit weird with the ester, so I'll redraw the entire thing. So an ester is 2 different chains stuck together, and this is the one that we learn how to build. Okay, we don't actually build it, just theoretically how we build it. So again, shock horror, start with an alkane. I know, amazing. We then make this carbon. So what we have with an ester, we have alkane, alkane, and then we're stuck something completely different. So you've got 2 separate chains of carbon stuck together on either end of this function. It's the only one where you'll see oxygen in the middle. I don't think I'm going to do any more than that today, because it's meant to be an introduction. Next week we will look at naming. For this unit, you only need to really know the alkanes, alkenes, and alkynes. We'll go through naming the other ones because they will throw the name itself into a question every now and then. So next week we'll be naming organic compounds. Then we look at all of the functional properties of how the functional group affects that. But it's all based on the same stuff. So if you can keep up each week and it makes sense, then you do it at school again, and then the next week we're a week ahead, everything should really stick. We'll probably spend the last 15 minutes of each session just doing practice exam questions. And I'll probably give some for homework as well if you feel like doing it. But that's how it'll be about 40 minutes of me spewing information at you, and then we will just smash out exam practice questions. Whether that's just me doing them for you, or if you guys want to interact, I don't know. We'll figure it out as we go. But thank you. I didn't do any seminars last term because I was too busy, but I made this for you guys because I know it's getting close to exam time. So I will see everybody next week. We'll see most of you this week at some point.